Hi everyone, welcome to Machine Learning with Python. We will be covering today most of the Python distributions, probability distributions, using Python. And Jamie Tosawa, our technical lead for the study circle, is going to go through this fantastic learning you will have on the machine learning and also on the statistics and probability distribution. So let's welcome Jamie Tosawa to take over from here. Jamie, go ahead.
Yeah, so thanks a lot for the introduction. So hello everyone, welcome to the Machine Learning's session 3.1, where we will be covering the concept of random variables in probability calculations and its role in analytics. Then the understanding of different probability distributions, common distribution techniques such as normal distributions, exponential distribution, Poisson, and their applications with different examples, and also how to derive insights from the statistical measures such as mean, variance, probability distribution functions, confidence intervals, etc. So let's get started. Next. Yeah. So why do we use probability? Before diving into the contents of the slides, why do we use probability? If there are chances of success for one choice, if we are given two choice, then we will be we'd love to have that insight, that which is the successful one. And if that's the successful one, we like to choose. We would like to have that choice as our choice. So this is what the probability means in a very basic and a common manner. Um, we 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 use it in different day-to-day lives and in sports and entertainment for different reasons. In sports, if you are a cricket fan, then we toss for decide who gets to bat first and ball first. And then so if for let's say we consider a playing ground where a number of probabilities of heads were more, then the captain of the team will have a choice or call a choice for its own choice of batting and bowling. So that's how we use probability in a day-to-day life. But there are different another applications of it which are done for the business aspect of in the field. So why do we choose why do we go apply or use probability? So using the analytics for deeper understanding, then testing a hypothesis and building models to explain variations in key performance indicator that is of importance to the business, such as profitability, market share, demand, etc. So there are some of the terms that we'll be first discussing before diving deep into the probability theory. And so some of the terms we'll be discussing, starting with a random experiment. If we start conducting an experiment and we cannot, or we do not know prior to conducting the experiment that what would be the result of it, we'll call it a random experiment, because we are not certain, or there is a randomness in the conclusion or the result of the experiment. Then there is the other term is sample space. So sample space is the set of all the results that we are conducting the experiment of will be containing its result under. So sample space contains all the results that are being conducted or the experiment. So it is represented by a capital or uppercase S, and individual outcomes are called the elementary events. If we are tossing one coin and we are getting heads, we can give it an elementary event. We can call it an elementary event. Then the sample space can be finite or infinite. Then examples of sample space are outcomes of the college applications. You can see admitted or not admitted. These two can be the only one. Then predicting customer churn, which is churn or no churn. Then television rating point, which is between a range as from 0 to 100. So, and as X is capital X is a real number that can take any value between 0 and 100%, and we'll be listening to it, discussing it more about further. So event is a subset of sample space, and probability is usually calculated with respect to an event. So what we are doing is called an event. So number of cancellation of orders placed on an e-commerce portal site exceeding 10%. Then the number of fraudulent credit card transaction exceeding 1%. The life of a capital equipment being less than 1 year. The number of warranty claims less than 10 for a vehicle manufacturer with a fleet of 2,000 vehicles under a warranty. So before moving further, let's just discuss few examples in order to get a good understanding of the random experiment, sample space, and event. So let's for first is one dice is being rolled, and what is the probability of it being rolled to 6 being up? Means 6 side, the side of 6 being up. So here the random experiment is called will be the dice being rolled because we do not know its outcome. Then sample space between sample space will be the set of 1 through 6, as those are the only choices that can happen. And an event will be as a an event can be anything, but as we have discussed of 6 being up, so here we will name the event A, where sixth side is coming up, and its chance and n of A equals to 1. Then similarly for the second example, in an exam of 100 marks, what is the probability of students scoring more than 60? So here the random experiment is exam. The sample space becomes marks 1 through 100, and event becomes a student scoring more than 60. Next is random variable. So anything that we perform an experiment on can be mapped to a label or a tag. So we'll call this a random variable. Any experiment's outcome to be mapped to a tag or a real number. So this plays an important role in describing, measuring, and analyzing uncertain events such as customer churn, employee attrition, demand for a product, and so on. So if the random variable, which is denoted by capital X, can assume only a finite or countably finite set of values, then it is called a discrete random variable. The credit rating, as you can see, there are different kind of credit ratings. It comes at AAA, AA, A, triple B, etc. The number of orders received at an e-commerce retailer, which can be countably infinite. Then customer churn, whether it's a churn or a no churn. Then fraud, whether it's a genuine transaction or a fraudulent transaction. Then it's a random variable with continuous values. So as before we had uh, we discussed about it that and if there are countable values, then those are called discrete random variables. But where it makes more sense to have a range to be counted, or at that time a continuous random variable has to be used, so or which contains an infinite set of values. So example of them are market share of a company, percentage of attrition of employees of an organization, then time to failure of an engineering system, and time taken to complete an order placed at an e-commerce portal. So discrete random variables are described using probability mass functions and cumulative distribution functions. Remember, cumulative distribution functions will be existing in both the continuous and the random, and we'll be discussing it separately. So PMF is the probability mass function is the probability that a random variable x takes a specific value k. For example, the number of fraudulent transactions at an e-commerce platform is 10, will be written as p x equals to 10. Then CDF is the probability that the random variable x takes a value less than or equal to 10, which will be written as p x being smaller than or equal to 10. The examples of discrete and random variables are credit rating, as discussed before, also AAA, AA, triple B, etc. The number of orders being received at an e-commerce retailer, countably infinite, 0 to 1 million billion, and smaller to LT crore integers. Then customer for churn and no churn, and fraud for fraudulent transactions or not, which are binary values, which means that fraudulent or non-fraudulent. So let's take an example first. Here we are discussing the PMF, which is probability mass function. So the sample space of 3 coins being tossed, and their results will contain any of these only. So our x will, or random variable, will be number of ways heads can result while tossing a coin. So there are total 0, 1, 2, and 3. There are only 4 things that can happen, or 4 ways the heads can come. So x1, which is 0, which means that no heads can come, which is when the case is all the 3 coins were tails. Then x2 for 1 heads, for 1 number of head turning up, and x3 for 2 heads turning up, and x4 for 3 heads total turning up. So you can also calculate the probability of those with their probability being represented at x equals to 0 through 3, and their respective probabilities from 1 by 8 out of the 8 choices, 3 by 8, 3 by 8, and 1 by 8. And if we add them all together, it will result into 1. Next is an example for the cumulative distribution function, which tells the probability that the outcome of the experiment is less than or equal to a certain value or a specific value. So let's say we are rolling a die and we are interested in a probability that the outcome is less than or equal to 3. So so below are all the results which can show up for whenever we roll a die. So if you roll 1, and its probability is 1 by 6. Then 2, if you roll 2, the probability of getting a value less than or equal to 2 is 2 by 6, because there are 2 values now, 1 and 2. Then same for 3, same for 4, same for 5, and same for 6. And as we have discussed about being 3 or equal to 3, less than or equal to 3, That's our answer, or the blacked out one. So the CTF gives you the cumulative probability up to a certain value. It's like adding up all the probabilities of getting values less than or equal to that specific value. Next is continuous random variables. So a random variable x, which can take a value from an infinite set of values, is called a continuous random variables. Example of them are market share of a company, percentage of attrition of employees, time to failure of an engineering system, time taken to complete an order placed at an e-commerce portal. So continuous random variables are described using probability density function and cumulative distribution function. So the probability density function is represented with the formula f of x equals to limit uh, theta x tends to 0, and p uh, representing x, the capital X being in the limit between the x and x plus theta x, which is a very small interval. Then the cumulative distribution function f of a for integration of minus infinity to a f of x dx. The random variable takes value less than or equal to a value a. So a equals integration minus infinity to a of f of x dx. That is the area under curve of f of x for less than a. So for its examples, uh, imagine you have a continuous random variable like a height of people in a population. The PDF tells you that the relative likelihood of random variable falling within a specific range of values. So considering the heights of adults in a certain population, and the PDF tells you that the probability density at a height of 170 centimeter is a 0.02. So it means that the likelihood of randomly selecting an individual with a height very close to 170 centimeter from this population is a 0.02 per unit of height. Such as per centimeter. So for continuing with the cumulative distribution functions, uh, another example is, let's say we have a set of these heights of these individuals in the from the population. So for a CDF f of x at a specific height x gives the probability that a randomly selected individual from this population has a height less than or equal to x. So for the given heights, as you can see, 160, 165, all the way through 190 with a step of 5, the number of individuals with heights less than or equal to 170 centimeter is 3, which is 160, 165, and 70, 170. So the total number of individual is 7. And if we go for the calculation, f of 170 becomes 3 by 7. So this can be generally denoted as f of small x equals to probability of capital X smaller than or equal to smaller case x, where x is the random variable as we denoted with uppercase x, and specific values are denoted with smaller case x. So cumulative distribution functions for discrete and continuous. So it is CDF in discrete is evaluated at each possible value of the random variable, but for a continuous, it is evaluated at any point within the range of a possible value of a random variable. So we'll start discussing the common distributions, and starting with a binomial distribution. So a binomial distribution is uh, discussed or used whenever there are binary choices of outcomes or binary outcomes, whether it's a pass or fail, a success as success and failures, and each of these trials are called Bernoulli's trials. So the objective is to find the probability of getting X successes out of n trials. The probability of success is P, and thus the probability of failure is 1 minus P. And the probability of P is constant and does not change between trials. Examples of them are churn and no churn, fraudulent transactions and genuine claims. Then, fraudulent claims and genuine claims, and a role uh, loan repayment of a default and no default for customers. So, as you can see that this is a graph of an e-commerce website of 20 customers, out of which purchase has been made from them, and we are trying to predict the probability of the number of items that can be returned. So you can see the at number of items returned for 2, the probability will go right about 30%. So you can also take this code and also uh, use it for forming the graph, and I will take over just for showing the graph. So for binomial distribution, we are discussing this example of an e-commerce platform of which sells women's apparel. So it is observed that 10% of the customers return the items purchased by them for many reasons, for color, material, etc. And on a specific day, 20 customers purchased items from the e-commerce platform. So what we'll be doing is we'll
Jamie,
calculate. Yeah,
Jamie, are you sharing?
yeah,
Can you share again?
yeah. I shared.
No,
Okay,
reshare,
okay,
reshare,
okay, okay.
reshare.
Is it visible?
Just a minute. Hmm. 1 sec. So you're viewing Jamie's screen. No, it's not visible. Can you reshare?
No, no. It will be.
Yeah, now it is. Now it is sharing. Yeah,
Yeah.
go ahead.
So starting with the probability that exactly 5 customers will return this, you can start using this. Uh, I'll simply tell you the code or highlight the code in order to get the output. So we get our um, uh, uh, needed packages, and then using this as using the same that we saw on the slides. This is the same graph for a number of items returned, and you can see the probability of them over here with PMF being showed. Then using,
What library are you using? You said assume
yeah,
library.
okay.
Which library?
So first were pandas, then matplotlib, and cborn. So these same libraries will be used for the rest of the presentation as well. So for binomial distribution, we can use stats.bino for CDF and input these values. For calculating the probability of a maximum of 5 customers will return 5 out of 20 and 0.1, and this is the probability that we gave. Then the probability that more than 5 customers will return the item purchased by them. And if we run this query, then we'll get the output. Now, average number of customers who are likely to return the items and the variance and standard deviations of the number of returns. A is the average of binomial distribution is given by n into p, and variance of the binomial distribution is given by n into p into 1 minus p. So these are the mathematical one, but we have the in the packages we have the features for us to get it calculated. So by giving the needed parameters, we'll get the average of 2 and variance of 1.8.
Can we switch over?
Yeah.
Just hold on. Okay. Yeah. So can you repeat what you started in the binomial distribution here?
So
What is
so
explain
for
this now?
yeah, so for the binomial distribution, we discussed about the number of returns that are made by the customers for on a specific day. So for 20 customers purchased items from the e-commerce website. So this calculates basically the probability of customers returning the items. So 20 purchases were made, and the probability of, as you can see in the graph, the probability can for 1, 2, and 3 is 1 and 2 can be seen more, and it almost reaches up to 30% of it. And if you want to specifically just recreate this this graph, then you can use the code which is displayed on the left side of it.
So can you explain what is this PD?
So PDs is we have imported PD as pandas. Pandas has PD, so we'll be using the alias PD for using whenever we use pandas. Then data frame is nothing but their the pandas library's way of displaying the data in a column and row form, which is
In
much
memory.
similar to
In
SQL.
memory, right?
Yeah, the
It's
in-memory
in
one.
memory. Okay. And what does this range describe?
So range as we are taking into consideration of 0 to 20, which will start. So the range is basically a function in Python, and the first value will be included, whereas we want till 20, and the last value which will be included will be the one that is specified before that. So if we want 20, then we have to specify 21.
Okay. And that was from the Panda library. Okay.
A range was for Python only, but
Okay.
the data frame was for pandas.
Okay. And what about this list stats?
Yeah, these are the commands. These are just codes, or the whole is a snippet in order to create the plot, bar plot,
Mm-hmm.
which is displayed on the right side of the slides.
Mm-hmm.
So
So plot PLT is plot here, y and x I can see, but
yeah,
is the stats also part of
the
that, or is it
first The stats were the part of the when I shared the screen, I showed the use of it.
Is it scikit or
Yeah, yeah. It's from Scikit. Just a second, let me just.
yeah? You can verify
Yeah, it's from SciPy actually. Sorry,
scipy.
not Scikit,
Okay,
SciPy.
okay, scipy. Okay. So the idea is you can have a distribution, and for a this is for discrete, right? That is
Yeah,
your,
yeah.
so you got 20 discrete events, or you are taking 20, number of trials is 20.
20 customers purchased. So those
Uh-huh.
are the customers, and the probability of them returning the item
Okay. So,
displayed through PMF.
so if 20 purchased, how many returned? Correct?
Yeah,
How many likely to return?
yeah,
It's a probability, of course.
yeah.
And so you have a success when they return, or
Uh,
number of items return. You are taking number of items as 20 return. Number of items returned out of 20.
so so the snippet that we are referring to right now, it it's for the uh, it's a part of the question which is which calculates the probability that exactly 5 customers will return the items.
Hmm.
So
Okay.
expected number of successful trials and
Mhm.
total number of trials and probability of success. Those are
Mhm.
the parameters that are given. So the
Mhm.
binom PMF will take 5, which is the expected number of successful trials. Total number of
Mhm.
trials are 20,
Mhm.
and the probability of success is zero point 0.1, which is 10%.
Okay. So it is this one. Okay. So this is a distribution. So again, just walk through the what is binomial distribution to. So number of.
So binomial distribution is used when we are the outcomes are in binary form, which is true, false,
Mhm.
success, failure, yes or
Correct.
no kind of
Mhm.
outcomes.
Correct.
So
So
the objective is
objective was to find the.
probability of getting X successes out of N trials.
So in that case, you are talking about 20 trials
Yes, and a
and
five.
five success.
Yeah,
So probability of getting five success.
yeah,
Probability is same. It doesn't
yeah,
change.
yeah.
Correct. So
Between
now
trials.
what I want is, now that you have understood this and you have explained it properly, what is this PMF function? Here is the formula. Explain what is
Yeah,
this.
yeah. So probability PMF is probability mass function as a binomial as a uh, uh, discrete random variable. So the PMF is represented with capital X, which is a random variable, and small x, which means the values. So n choose x or NCR or n over x into p raised to x into 1 minus p, the whole raised to n minus x, where n over x is equals to n factorial divided by x factorial into n minus x whole factorial.
So is this combination or
Uh,
permutation? It's a
this is
combination.
this is for per- permutation, and we'll be discussing it for further also.
Okay. So, okay. So, okay. Go ahead and. What is this then? Lower one.
Just a second.
This is for the PMF, right?
Yeah,
And that is probability mass function.
yeah,
And this is for binomial distribution, discrete variable, right?
yeah.
X, X out of interest. Now here, the CDF formula here given is for X less than equal to X, right?
Yeah,
And that is nothing but shown as summation.
yeah. So,
Okay. So what is the difference between this and this? Here it is equal to,
yeah,
here it is less than equal to. Correct?
yeah. So the above in the PMF, it's the combination, which is CNX, which
Mhm.
is n factorial divided by x factorial into n minus x whole factorial.
So it's not probability, it's combination. Okay.
Yeah, the
And that multiplied by the probability and 1 minus probability
yeah,
of whatever
yes.
the event. Okay. So what is this now?
So this is the cumulative distribution function of the binomial distribution, and it's the formula to it, which gives the summation of starting with k
How
equals
many
to
events?
0 through x.
So x was equal to x here, is x is less than equal to x. So there are
Yeah,
more
it's
events here. It's a
yeah,
distribution.
yeah. It's rather showing a range to
Yeah.
less
Good.
than or being equal to a specific value, which is here represented by the smaller x.
So the stats came from SciPy, correct?
Yeah,
Okay. So I just wanted to go back and so you have you started with common distribution,
yeah,
binomial. Binomial means you got success or failure,
yeah,
right? For random variables, two
yeah,
outcomes only, right? If
yeah.
you have more than two outcomes, then what happens? Then this is
Uh,
not the distribution, right?
yeah.
Then you move on to
Different, and there are various different distributions that
mhm,
can be used
mhm,
depending on the use cases
mhm.
and what we need out of them.
Yeah. So here it was a success or failure for binomial. Binomial
Yeah.
means two, right?
Yeah,
One of the two. But if it is more than one of the two, it can be a number, right? It could be three, four, five, whatever.
yeah, yeah.
Such a distribution, which one you use then? Yeah, go ahead with Poisson.
Uh, yeah, yeah. So Poisson distributions are used when we want to express the probability of a given number of events occurring in a fixed interval of time. So, so there will be a use of a rate of occurrence, as if you see when we say come to the formula. So the formula for Poisson distribution is capital X equals to k, where uh, which is equals to e raised to minus lambda. Lambda is nothing but the rate of occurrence of the within a fixed interval of time, usually time, and so e raised to minus lambda into lambda raised to k divided by k factorial. As you can see, lambda is the rate of occurrence of the events per unit of measurement. Usually it is done on time, but it can be some other events also. And then the examples of Poisson distribution are a number of printing mistakes per page, then dishonored checks at bank, cancellation of orders by customers, then customer complaints, cash withdrawals at any ATM, typographical errors in a book, potholes on roads, etc.
So all these are numbers, right?
Yeah, the rate of occurrence in a way. Yes,
Rate of occurrence. So what do you see?
numbers are measured on rate of occurrences in that way.
Okay, rate.
Yeah.
number as a rate,
Yeah.
periodic, within a period.
Yeah.
Okay. So this is some call
Yeah.
received.
So
Yeah,
yeah.
go ahead.
So this is also belongs to an example that we'll be discussing for the Poisson distribution.
Uh-huh.
So so
So without going to code, what do you see here?
so so this is as I know the whole example. What this is saying is the lambda here is not greater than 10 calls per slot, and we are taking into consideration uh, uh, so here the value of lambda is 10, and we are taking into consideration a 3-hour period, so
Okay.
which makes the range from 0 to 30 or 0 to 29 to be specific for a representation of this, as we are using the range function of Python. And over this 3-hour period, or a 30 or
30.
30 slots, sorry,
Mhm.
30 slots, what we are trying to predict is how many calls are likely to be over a certain time for the calls received. So
So each slot not greater than 10 calls per slot, right?
yeah,
So everything less than 10 calls, 1, 2, 3, 4, 5, 6, 7, 8, 9
yeah,
calls maybe,
yeah,
or 10 calls. If you
yeah,
exceed 10, then it is it's not counted, right?
yeah,
It's not
yeah,
counted as success.
yeah.
So it is a discrete, right?
Yeah, this is a discrete probability mass function being used to represent it, this example and discuss it.
So what was this which we saw in binomial previously? Same, we are using data frame, correct?
Yeah, we are using the pandas data frame, where we'll use the success range 0 to 30 as described for before. Then we'll be using the Poisson.pmf function in the given range.
So this is supplying 30 slots with no not greater than 10
10 is
as
the value of the lambda.
okay. So that's why. So you are giving the parameter lambda 10 and
Yeah,
you are giving the slot time 30
yeah.
and you use the
Stats dot,
SciPy's
yeah,
SciPy
SciPy
stats
dot
to get the
Poisson.
value, to
Yeah,
get the value. And then after getting the value, whatever results it gives you, the distribution PML DF, you are trying to do what? Display it
yeah,
as bar graph. Correct?
yeah, yeah. So
So this is your C-bond, right? What is it?
yeah,
SN is
Sn
C-bond?
is C-bound. So Sn dot bar plot uh, will uh, will help us plot the graph and given
Hmm.
the needed parameters.
Hmm. So the parameters are X and Y. X is the success
Yeah,
and Y is the data frame of PMF to plot.
yeah.
Okay. And then what do you do? What is this?
So and that is nothing but the label of the x-axis that is appearing as a number of calls received.
Okay, good. So now this is Poisson distribution. Now can you
Yes.
go to your code and explain on that?
Yeah.
Yeah, you can share now. Go ahead. Yeah. So you're doing it under Jupyter notebook?
Yeah. This is the Jupyter notebook.
Hmm.
Uh,
Okay.
so these are the same contents that were discussed for the Poisson distribution on the slides too. just for the reference purposes, these are kept over here too. So as a Poisson distribution uh, try expresses the probability of a given number of events occurring in a fixed interval of time, with this being the formula of e raised to minus lambda into lambda raised to k divided by k factorial, where lambda is nothing but the rate of occurrence. So for a Poisson distributions, we'll be discussing an example of a call center receiving 10 calls per hour. So the lambda's value becomes 10. So first query related to that, what we'll be discussing is calculate the probability that a maximum of 5 calls will arrive at a call center. As the number of calls arriving at the center follows Poisson distribution, we'll use a stats.poisson.cdf, which is nothing but the Cyber library's function of Poisson CDF to calculate the probability value. It takes following two parameters. The first parameter, the number of events, in this case are 5. As we are discussing about the 5 calls, the first parameter is the number of events, which are 5, for which the probability needs to be calculated. Then second parameter is the average number of events, which is 10 calls per 10 calls per hour. So giving these values, and we'll get these results. Next is to calculate the probability that the number of calls over a 3-hour period will exceed 30. So since the average calls per hour, which is lambda equals to 10, we are interested in finding the calls over 3 hours. The mean number of calls over 3 hours is a lambda t equals to 30. So giving this into the 1 minus stats.poisson.cdf and giving the values of 30, 30, we'll get these, get the 0.45 value for it. So there is a 45% chance of it. And if we try to plot the to visualize the Poisson distribution for the average calls per hour as 10, and so for the 0 to 30 range, we can create this bar plot. So for this, you can this is the same code snippet that was discussed on the slide. So
Yeah.
PMF DF, the pandas data frame being used for the range is 0 to 30. Then stats.poisson for the Poisson distribution calculation, and then plotting the graph on it for the success over here, and PMF DF.
Okay.
Then
So,
the X labels being displayed over here.
yeah, let me ask you to stop sharing. I will go ahead with the. So you finished. Are you able to see or no? Yes, no.
No.
Okay, let me share. Okay, so here we go again. Share. You're able to see now? Yeah. Continue.
Yeah.
So is this the one you wanted to do?
Uh, uh, just
Poisson is over, and we
yeah,
started.
exponential.
Yeah, go ahead.
So starting with the exponential distribution, it is a single parameter continuous distribution that is traditionally used for modeling time to failure of electronic components. The exponential distribution represents a process in which events occur continuously and independently at a constant average rate. So the examples of exponential distributions are amount of time until a a certain event happening, an amount of time passing by, and again that event happening, and until that a constant average rate is being maintained. So you can put those events for anything that can be suitably applied to it. Here you can see in the example that the amount of time until an earthquake occurs has an exponential distribution. The duration in minutes of long distance business telephone calls, then amount of time in months a car battery lasts. So the exponential distribution is widely used in the field of reliability, or testing the structural failures and stuff. So reliability deals with the amount of time a product lasts. So EMF of exponential distribution is given by the formula f of x equals to lambda into e raised to minus lambda x, where x is greater than or equals to 0. Here lambda represents the rate of occurrence of the event, and the mean of exponential distribution is given by 1 by lambda. So imagine a system and its success rate while it is manufactured or produced or constructed, and then its um, success rate over the period of time. So this is the same plot being displayed in the graph for the number of hours. So you can see the success rate of it being high for 100 hours, and then over the number of hours till 4,900 or 5,000 to be specific, if we uh, account to the code values, and then 0 through 5,000 hours, you can see the success rate of a system being plotted on the graph. So we are using the pandas data frame for success, then having a range of 0 through 5,000 with a step of 100, and then using the exponential function of scipy on them and giving them the values. The seedborn bar plot for plotting the graph, as well as x sticks and x labels for the labels and their rotation or orientation, or the angle for them being displayed.
So, just to clarify, uh, so you mean that time to failure, the probability of the time to failure is
Increasing with time.
increasing with time. Okay.
The plots are for success. So you can see at the beginning
Yeah.
of only 100 hours,
So
it's very
it is
successful.
not failing. It is not failing to failing.
Yeah,
Okay, good. That's what I wanted to clear, because when you time to failure, it says time to
yeah,
failure is highest. That is 5,000. More likely that it
yeah,
will fail here than here,
yeah.
early stage. Okay, good. So I don't think we need to code for this. You can just skip, go to the
Okay.
normal distribution.
Okay, so normal distribution, one of the really common distributions which we can see in our day-to-day life, and its application can be uh, seen if we try to see it or try to plot it. Also known as Gaussian distribution, a function that represents the distribution of many random variables as symmetrical bell-shaped graph. Uh, uh,
Okay. So have you switched from uh, discrete distribution to continuous distribution?
No,
Does this
those
apply?
will be the part of these distributions wherever they are applicable.
Mhm. So normal distribution is applied to continuous variable, random variables, or discrete, or both.
It It,
It is
with
applied to
the
continuous, right? Because you are taking a variance
yeah,
in
yeah, because we
standard
are
deviation.
taking a curve and we are trying
Yeah,
to see
yeah.
the values over. It depends on the use
So it
case.
will be PDF. It will be PDF and not PMF, correct?
Yes, yes, it will
That's
be
all I want.
probability density function.
Okay, good.
Yeah,
Explain here what is this diagram.
yeah. So uh, so this is how the as in the diagram you can see that this is how the normal distribution functions are displayed with their percentage of distribution being displayed with 34, 34, and 13.5 to 13.5 and all. So there is also a single tail and double tail, which a single tail basically means that it's starts from left side of the graph. As you can see, the from where the left side of the graph starts increasing, and those are mostly represented with a minus sign before the value, and that on the same counterpart of on the right, or its counterpart is with represented with no sign or plus sign if someone wants to be really specific. So the normal distribution is observed across many naturally occurring measures such as age, salary, sales, volume, birth weight, height, etc. And also in the diagram, I would like to come again there, which also displays the mean and the standard deviations being represented for showing the portions or division of them, where a mean being the middle, then a mean plus and minus of a standard deviation consisting of certain portions, then mean plus or minus of two times the standard deviations consisting of certain portions and etc. So a normal distribution, as we have seen in the previous, it is also known as a spherical, a symmetrical bell-shaped curve, or has a bell curve. So it is also known as a bell curve. And to understand the normal distribution, we'll also take a solid example of BSE, which is a Bombay Stock Exchange. Take its two of its stock, which are BEML and Glaxo, and we'll see different things related to them. And for this discussion, even though we'll start with the open and closed price and their fluctuations in prices over the time, for this explanation of their example, we'll be taking into consideration only their closed price. Um, okay. So
So what are you
this
doing
is a
this? Go ahead. Yeah.
yeah. Sorry. So this is a graph being plotted for the gain of the two stocks that we discussed of Glaxo and BEML. As this is a density graph, and also shows the gain that the respective ones have made. Um, and you can see how we are calculating gain over here, which is gain equals to close price T minus close price T minus 1, which just basically means that the close price of the previous day uh, to the close price of the present day, divided by the close price of the previous day. The Seaborn's library is used for plotting the graph, for Glaxo and BEML, and then and giving them the labels and seeing the site insights, what we can make out of it.
So before you move, so
Yeah.
what was the distribution? Was this for period
This is
starting from 2010 to 2016? Is that what it is?
no. The overall one is not over here. It's on
Mhm.
the notebook. This is just a gain showed on a particular day.
So this is only broad part of it, not the calculation part of it.
Yeah,
Calculation
in a
is
way.
done. Yeah. So this is normal distribution, but how did you calculate is the question. Can you go to your
Yeah. I
and
will. I'll be.
yeah, I will just maybe I should stop sharing myself, or you start sharing now.
Yeah, I'll start it. Can you see it?
Yeah, I can see it. Go ahead.
Sure. Yeah. So, as discussed, for the for the normal distribution, we'll be taking into account the two stocks from the BSE, which is Bombay Stock Exchange, BEML, and Glaxo. So first, we will be importing the pandas library, SPD, PD, and PD, numpys as NP, and warnings for their respective users, and we'll be importing PD and NP as their aliases. So first we'll be reading the .csv file, which is comma separated value files for BEML, and then displaying their first 5 results, 0 through 5. So you can see the result that is being displayed over here for that. This is for BEML. The same we will be doing for Glaxo as well, and this is the result that we get.
So is this on a month basis or day basis or what is it?
The dates are given. These are
Okay, daily.
daily ones. Yes.
So on 2010, 1st January 4th, 5th, 6th, 7th, 8th.
Yes. And their
Okay,
open, high, low, last, and close price and stuff are
okay.
given, and the turnover on in lakhs and total trade quantities.
So out of which, what are we using? Close pricing?
Yeah, so we'll be only using the close price for this explanation of the
Okay,
example.
okay.
So as just said, that we'll be only using the close price of both the BML and the Glaxo. So we'll be doing this with this, and within the pandas library, we'll be doing it.
So is this a column or a row or column and row? Which one is
the
this? Which
the
is
the
columns
column,
only?
yeah, the columns are selected for their
Mhm.
respective uh, stocks.
So that means two stocks are being monitored by column, which is date and closing value. Okay.
Yeah. Okay. So so you can see the after deciding the date and the close price. This is how the Glaxo's data frame that we just created over here
Mhm.
is looking like.
Okay. Good.
Yeah. So for further explanations, we will be using the Seaborn library as well as the Matplot library will be imported, and they will be given the alias of SN and PLT. Matplotlib for PLT and Seaborn as SN. For plotting, we'll be using the LexoDF close for and time and close price given as the label for X and Y respectively. So this is for Glexo, and This is how the graph has been looks like. So you can see for 2010, it started to rise up. Then in 2013 to 2014 around, it went up and took a dip, and after 2014 it again started going up, and in 2017 it is showing a downward direction again for the plots that we have taken for Glaxo. The same if we do it for remember we are doing it for the close. So doing it for doing the same or similar things for the BEML stock. For 2010 uh, 2010 to 2013 it majorly went down while showing some of the uh, up movements, and from 2013 to 14 it kind of stayed in a similar space, and then moved up since 2014, and in 2014 to 2017, and though it took its peak in between 2000 mid 2015, but the stock is again rising in 2017. So uh, just a second. So shall I go for the explanation from here, or shall I continue on the
Yeah,
slides?
you already gain you have explained, the gains, ups and downs you explained.
Yeah.
Continue on the, is there anything more than that? What
Uh,
is this graph and that graph, two graphs, are they related? How do
yeah.
you,
These two are for two different stocks, which I explained.
yeah, okay. Then further, is there anything, combining the two, is there anything to be shown?
Not combining, but this is using the same graphs. Sorry, same stocks. We'll be
Mhm.
discussing a different way of them,
Okay.
which is for
So
the gains that we found.
do you want me to switch over back? Or you have something to
Just a
say?
second. Let me. Okay. Let me just explain it over here only.
Mhm.
So, uh, so let's say we are taking into consideration short-term tradings or intraday
Mhm.
tradings for an
Mhm.
investor, and trying to understand the following characteristics of the stocks. What is
Mhm.
expected daily rate of return of these stocks?
Mhm.
The which stocks have higher risk or volatility as far as daily returns are concerned? What is
Mhm.
expected range of return for 95% confidence interval? We'll see
Mhm.
what is a confidence interval, and confidence level, etc. Which stock has higher probability of making a daily return of 2% or more, and which stock has higher probability of making or less loss of 2% or more, loss or risk of 2% or more. So for the gains, we have seen on the slides as well as over here. This is the formula that we will be using. Uh, Close price minus close price of the previous day divided by the close price of the previous day. And using the same gain, we'll be doing it for the both the stocks, which is Glaxo and BEML, and using the data frame that we created for both of them. And if we see, uh, we are displaying the first 5 results of Glaxo over here, and the gains that it made using the formula. So these are the gains. Some are minus, some are and positive, etc. So, and you can see the first is NaN because it does not have a previous value to refer to. Then now for Glaxo, let's plot a graph for the time and gain. Uh, these are the X and Y labels, and these are the plots and the figure size of 8 and 6 that we'll be using. So this is the plot of time and gain for Glaxo. It peaked for around zero point 0.2 gains in 2014, and also took a dip after some time before 2014 and after 2014. And if we want to compare the gains of BEML as well as Glaxo while overlapping them, we can plot using his plot, which is this, to plot them or to overlap them one above the other and show their pattern.
So pattern is distribution, right? In this case.
This is density.
Yeah. Okay.
Though
Density.
the plots are given in that way, but this is density.
Yeah, that is normal distribution.
The the yeah
Yes, we
this is
started with normal
yeah
distribution,
this is
right?
for
And
a normal. The whole stock is used for explanation of the normal distribution only.
good.
Okay.
That's good.
Yeah.
Anything else is there in this?
No, yeah, I'm just so just to summarize. So as if we have overlapped and saw the performance of both over here and see how we can do it. After that, let's try to have a mean value of both the stocks, daily gain of Glaxo, and then standard deviations being used. And if we put these values, then we can get the values of Glaxo for mean of 0.0004 and a standard deviation of 0.03034. If we do the same for a mean and a standard deviation of the stock of BEML for daily gain of BEML, then we'll get the mean of 0.0003 and standard deviation of 0.0264. And if we want to summarize it for both the stocks, then we can use the describe method in order to summarize.
So these are the functions you are describing available
Yes.
to you. But what are the meanings of these? Can you go back to the original slide? Can I go back to original slide and you explain that?
Uh, I,
These
I
are all
think,
calculations, right? You are going to calculate using some library.
yes.
So let me, if there is nothing more than that, go to the bottom, go till the bottom on this. Is there anything other than that?
Yeah, there are a few things.
Okay. So before you go to few things, can you go up, stop at stop here. Yeah. Just
Okay.
stop here and let me just hold on. Hold on.
Yeah.
So what I'll do, I'll stop sharing and then get the share again back. Okay. So before we go further, we finished with the normal distribution, right?
Yeah.
And in that, we wanted to have what is the definition of all this, what you're talking.
Yeah.
Can you go over this before we jump there?
So shall I start with the mean and variance? That's what you're.
Correct, correct.
Yeah.
Yes,
Okay. Okay.
it's a mean. All the definitions of what you are trying to explain there.
So,
Mathematically, you are trying to show this is doing
yeah.
this. But what is mean, median, mode? What is standard
Yeah.
distribution? What is variance? Explain that.
Yes. So mean is also known as average as uh, we might have seen or calculated or used in mathematics more. So it is calculated by adding all the numbers, or all the observations by divided by number of observations is a common term. So you can see the example of it, 76921, where number of observations are 5 and addition is 25. So we get the mean of 5. Next is a median, which is the middle value in the list, calculated by ordering the numbers from smallest to largest and taking the middle number. And if it's a even number of it, then the middle two are given, and their average is taken, and that becomes the median for us. So for the same observations, which are 7, 6, 9 to 1, the median would be 6. Then coming to mode, which is the most number of occurrences in the list. If here, imagine that instead of 6, there are 2 6s, then 2 or 3 6s, then 6 would become the mode over here. Then coming to standard deviations, which is a measure of how dispersed the data is in relation to the mean, which is average. So how much the data deviates from the average value. So low small standard deviations indicates data are clustered tightly around the mean, and high or large standard deviations indicate that data are more spread out. Then what is standard deviation? So this is just just a second. So what is the standard deviation? This is just an example. So for the given numbers, so if we calculate it directly, it will give out the answer of 2.29. But the way we calculate standard deviation mathematically is by taking the square root of average of the squared deviations of the values subtracted from their average value. We can refer to the formulas for a more clear explanation to it. So though here it is the
Before,
okay. So before moving to the variance, the variance is nothing but the square of the standard deviation. As a standard deviation is signified by sigma, so variance is represented by sigma square.
now go back to your, before we move to probability and all, finish the statistics portion on your,
Okay.
go ahead, share yours.
Can you see it?
Yeah, go ahead. Yeah, I can see it. Now,
Yeah.
now tell about what you were trying to show, mean, standard deviation and all that. Yeah.
Okay. So for the mean and standard deviations for the given stock price, this is how we can do it for the value of 4 given, and the calculated mean and standard deviation for Glaxo are these. The same thing if we do it for BEML, then we'll get these values. And if we want the overall summary of both the stocks for them, we can get it using a dot describe method. And if we pass each of the data frames with the gain on describe, then we can get these summaries on the respective stocks. The first one corresponds to BEML, and the second one corresponds to Glaxo.
Can you go back to the graph, previous page? Yeah. Now show me in this what is the what is this distribution and what is this? Where is sigma in this? Where is standard deviation and where is variance?
So, uh,
So how do you correlate between the this is a normal distribution,
so
Gaussian or a bell curve distribution, right? So
yeah.
what does this mean? This and this and this and is there anything? So you had go back to previous. You had shown 34, 34, 68%, right? Somewhere. Go back.
Uh,
Do you have the diagram or it's not here?
just a second. It's not here. It
Yeah.
over here.
Yeah. So what is this? Normal
So this is
distribution,
the
right?
yeah. This is the normal distribution.
So what is this 34, 34, 68 here, right? And here
Yeah,
you had,
yeah.
so what was this mean? Mu is mean.
Mu is mean.
Hmm. And this is mu minus.
Sigma is standard deviation, and
So, so 1 sigma, 2 sigma, 3 sigma variation from the
yeah,
mean.
these are the um, ways that the portions are can be covered. So
Yeah.
um,
So, so when you say 68% and when you say 95%,
yeah,
all these are related to what?
the uh, uh, that number of that amount of uh, portion is being
Confidence.
covered by them.
Yeah, confidence. You are confident that probability
Yeah,
that 68%.
these data points will lie within them. These number of
Yeah.
them.
Yeah. So the relation between the standard deviation and the mean is how much deviation from the center. Plus minus 34 is 68%. And that gives you a level of confidence based on what.
So,
So what is this? What
so
is this axis? This is gain, right? What is this axis? Can you go back to your diagram again?
this,
Yeah. So density,
yeah,
and this is gain.
yeah.
So you are
So for the mean, you can see that these are product of mean 0,
Mhm.
and
So if I take a 68% here as the density,
so,
am I right?
yeah, okay, okay, yeah,
So confidence level of 68, if the PD in this case is PDF, right? If the density function is showing 68, that means you are within one standard deviation. Your
yeah,
mean is
yeah.
zero,
So
right?
so
Mean is at the center.
yeah. So you can on the gain also you can see the minus 0.05 to 0.505,
Yeah. So
and
that
those
is
are
equal
the
to.
portions that are being covered by the respective stocks for
Mhm,
the respective gains.
mhm. So there is a relation between the density and the variance for a
Yeah,
bell curve,
yeah.
and
So
which is
uh,
standard.
yeah, so you can see that BEML, which is showed here in a more orangish tone, has a
Mhm,
more higher variance than the
mhm.
Glaxo's stock.
Correct. So it does represent something, right? The normal curve, bell curve,
Yes.
gives you the how dense it is, how it is closer to the mean or away from the mean. The distribution, basically,
Yeah.
using the PDA. In this case, it is PDF. Density function
Yeah.
reflects the variation from the mean By how much standard deviation? 1, 2, 3, and depends on that the confidence level, right?
Yes.
Okay, go ahead and explain what is confidence level. If that's the next, right?
Let me see
Yeah,
first
yeah,
whether it's on
yeah.
the uh,
Yeah,
uh,
it is. Yeah, just
photos.
go up, go up, go up a little, go up a little.
Okay. So actually, I have more contents on the slides for the
Yeah,
confidence
yeah.
level.
Go
So
ahead.
I'll
Yeah,
use the
you can.
slides.
Mhm.
So with so so whenever we talk about the probabilities and stuff, we they do have a certain pattern to it. And when we talk about the normal distribution, and then we want a certain kind of confidence when we are trying to make a decision. So this is what the confidence level as well as the confidence interval means. The confidence level in certain intervals can increase or decrease depending on where they are. So to find out what is expected range of a return for a 95% confidence interval, we need to calculate the values of gain for two standard deviations away from mean on both sides of the distribution. That is uh, as mu, which is mean, plus or minus 2 of its standard deviations. So it becomes the 95% of it and the portion of
So
the area
34
under
plus
the
13
curve.
point. So if you add 34 plus 13.5, how much is that?
34, 34, 7,
37, 47.5. 47.5
47.5.
into 2, with this plus minus both sides, 47.5. So that becomes
Yeah,
95%.
90. Yeah,
So 68%, 95%, and if it is going to be uh, 3 standard deviation, then that will be another 4.7 added to it.
yeah.
So there is 99.7%. You want to have be confidence level, then you must go 3 standard deviations.
Yes,
So usually you will find 68, 95, and 99.7. These are the three usually figures used by most of the analysts, right? For the predictions, market prediction example.
yes.
Okay.
And
So, and this can be for any other application, not necessarily only the stock
Uh,
market.
yes, it depends on the use case, and most of the patterns in the day-to-day life can be represented using the normal distribution.
All
So,
almost all natural, right?
yes, naturally occurring ones.
So let me. You have nothing more on this one, right? At this time, let's go back to. Let me stop. Uh, Let me just take over. Sorry. Let me again come back to sharing. Okay. So yeah, now you come back to where we are. After this, we had some formulas.
Yes. So, so for permutation and combinations, that so some of these aspects are used, or some of these parts are used in the probability formulas and stuff and that we have discussed till now. So first is permutations, where the the way you enter things, or enter the order of anything matters. For example, you can see the lock and its secret code. So even if there are two digits out of 10, 2 9 and 9 2 cannot be same. So if the password is 29 and you enter 92, then it will be an incorrect one and won't unlock the locker. So similar is the example for combinations, where actually the way you add the ingredients, for example, in a fruit salad, uh, if you add three fruits, apple, um, ma- mango, or
Banana.
whatever, yeah, banana, whatever, uh, in whatever manner, if you enter them in any of this, it is a combination and it won't matter the order in which you place it. So for NCR, as we have also discussed for the for the formula of n over x, in that case, was here we are choosing from 10 fruits, three to do it with. So for n factorial divided by uh,
N
x
minus R.
x into n minus r factorial. So for that we get the value of 120, and if we go to the permutations answer, then we get the for a permutation of 10 to, we get the value of 90. And for the given formulas, we for repeats and no repeats, which are for permutation where repeats are allowed, it's n raised to r, and for where repeats are not allowed, it's n factorial divided by n minus r whole factorial. For the combinations, r plus n minus 1 whole factorial divided by r factorial into n minus 1 whole factorial. Whereas for no repeats in combinations gives n factorial divided by r factorial into n minus r whole factorial.
Okay, so uh, we are done with that. And standard deviation is calculation.
Yeah, so this is the formula for the standard deviations calculation, where for first,
Sigma.
yeah, which is denoted by sigma or Sx, then which takes the square root of summation of starting from I equals to 1 to n, uh, where xi minus x bar whole square is divided by n minus 1, where n is the number of data points, xi is the each of the values of the data, and x bar is the mean, or we can also use mu if you're comfortable with it. And the normal distribution curve, you can see the same combination of mean with the standard deviations, mean at the middle, and then mean plus or minus the standard deviation. So continuing with the confidence interval. Interval is a statistical measure that provides a range of estimates within which an unknown statistical parameter is likely to fall. It is calculated at a selected confidence level, which represents the probability of the confidence interval contains true parameter values. It indicates the reliability of the estimation procedure, not the certainty that a specific interval contains the true values. For example, 95% confidence level means that in repeated sampling, the 95% of the intervals would include the population parameter. Moving to the confidence level, describes the uncertainty associated with the confidence interval. It signifies the proportion of confidence intervals constructed at the chosen confidence level over many independent intervals that will contain the true parameter value. For example, a 95% confidence level implies that 95 out of 100 intervals constructed in a same manner would contain the population parameter. So, example of a confidence level and interval for a customer satisfaction survey. Uh, Company conducts a customer satisfaction survey and asks 50 randomly selected customers to rate their satisfaction on a scale of 1 to 10. The sample mean of satisfaction is 8.2. Using 95% confidence level, you can calculate a confidence interval for the true mean satisfaction rating of all customers. The confidence interval might be, for example, 7.8 to 8.6, and meaning that 95% confident that the true mean satisfaction rating of all the customers lies between 7.8 and 8.6. In the example of coin flipping, if there are 55 heads of 100, then the interval is 0.45 to 0.65, having the 95% of it confidence level. Same for the heights of students. If measuring the heights of 20 randomly selected students and calculate the sample mean height as 165, then the interval of 162 and 168, meaning you have 90% confidence that the true mean height of all students lies between 162 and 168. So this is the explanation of some of the code executions that we'll be doing for the interval. So the interval method is used in stats.norm for giving the confidence interval of a normal distribution, which will be taking the three parameters, which are alpha, log, and scale. Alpha for the confidence interval, log for the location parameter of the distribution, which is mean for normal distribution, and then scale parameter of the distribution. It is standard deviation for normal distribution. Next is a cumulative probability distribution, which represents the probability of a random variable taking on a value less than or equal to a specific value. So it refers to the probabilities associated with different outcomes of a random variable. For discrete, the cumulative probability table is often used to organize outcomes of their probabilities, facilitating the calculation of cumulative probabilities for specific values or ranges. This table accumulates the probabilities as outcome increases and the cumulative probability summing up to 1 at the end. And understanding the cumulative probabilities is essential for assessing the likelihood of specific events or values occurring within a given distribution. As also discussed before, the function of a cumulative probability distribution is represented with f of x equals to limit of p tends to theta x tends to 0, theta x tends to 0, where
It is delta x. You call it as delta x.
oh, okay,
No,
delta
not
x,
it's not theta. Yeah, that's okay.
delta x
Yeah, tends to
tends to
zero.
0. So, and the value of a random variable capital X lying between the value of x to x plus delta x. And you can also see if there is a function a and its graph is being plotted. So f of a will have this area which is darkened in the graph. So to calculate the probability of gain higher than 2% or more, we need to find out what is the sum of all the probabilities that gain can take values more than 0.02 or 2% in a way.
So this brings to end. Yeah, go ahead.
Yeah. So probability distributions were discussed, where we discussed about the common distributions of a normal distribution, Poisson distribution, and then exponential distribution, etc. The other important distributions are beta distributions used for continuous distributions, which can take the values of between 0 to 1. Then gamma distributions for model waiting time, which models waiting times in different contexts until until the next n events occur using gamma distributions. Then Weber's distributions, which uh, it's a exponential distribution is a special case of Weibull distribution. In exponential distribution, the rate of occurrence of an event is constant, but using Weibull distribution, we can model increasing or decreasing rates of occurrence of an event over time. So in exponential distribution, we only took the constant rate of occurrence of an event, but in Weibull distribution, we take into consideration the increase or decreasing rate of occurrences of an event over time. Then geometric distribution for calculating uh, how many trials until a success happens, or how many uh, uh, yeah tries until a success are happening. So
So
compared to the binomial distribution, which encases the how many successes, the geometric distribution is about how many failures until a success happens.
so that brings to end.
Yeah,
Fantastic. Excellent job. And I would say it is a statistics and probability are difficult, and definitely it's a lot of coding as well. So glad to see that you have been able to explain the Panda distribution, Panda data frame, which is used along with the matplot and SciPy, various libraries uh, to be able to plot them. And obviously, this can also be done in scientific using R. But since our machine learning is with Python, we have focused on using the Python libraries as much as possible, and hope this gives brings to at least the statistics and probability portion of it. The hypothesis testing will be the next session. So I think we will call off today. And if you have any questions, please post them or send it to info at eotf.in, and we'll have this passed on to the study circle of Jamit to answer it. And we thank Jamit for the efforts. It's really a wonderful effort from his part, and congratulate him for completing this uh, statistics and probability, which is used in the machine learning with Python.
thanks.
Thank you very much, and I will stop recording here, and we will see next week, or next maybe Wednesday or Saturday, whenever Jamit is ready for the next session.